You've got 5 minutes until the bus arrives, and you've misplaced your keys. Again. They could be in yesterday's coat pocket, on your bedside table, in your dog's secret chew toy stash, or literally anywhere inside the house. In the classical world, there's only one way to find out. Check each place one by one. If there are n possible locations, the worst case is you ask n questions. That's O of n query complexity, linear time, and time that'll cause you to miss your bus. But in the quantum world, things can get more exciting. Quantum computers can perform a search using Grover's algorithm, which needs on the order of square root of n steps. That's massive speed up for big N. In a quantum computer, you start by preparing a state that represents all locations at once. Putting all locations in superposition doesn't mean your keys are magically in every single location at once. It means the quantum computer is temporarily considering all locations in parallel. But here's the catch. When we actually measure a quantum state, it doesn't stay in that parallel world. It collapses to one definite answer, one of the basis states, like table, pockets, or doghouse. Which one we get is not deterministic. It's random, but not equally random. Every state in the superposition has a number attached to it called an amplitude. The square of that amplitude is the probability that the measurement will pick that state. And Grover's algorithm works by pushing up the amplitude of the right answers and pushing down the amplitudes of the wrong answers until the correct location becomes overwhelmingly likely when we measure. Grover's algorithm relies on a special quantum operator called an oracle. Its job is simple. It flips the sign of the state corresponding to the correct answer, and it leaves all the incorrect answers unchanged. You can think of this like putting a secret mark on the correct location that only the quantum computer can use. Now comes the clever part. All of our states live in a kind of two-dimensional space spanned by the correct answer and all the wrong answers. Using two reflections, one reflection over the incorrect state and one reflection across the average of all states, the quantum computer performs a gentle rotation of psi towards the key's direction. Visually, it's like moving a pointer a little closer to the right answer each time. Each round of these two reflections is called a Grover iteration, and every iteration makes it slightly more likely for the correct answer to appear when we measure. Do this approximately a square root of n times, and the state becomes almost exactly keys. This trick of alternating rotations to rotate a vector is the heart of Grover's algorithm. Finally, you measure the quantum state. Because the algorithm has amplified the correct location so strongly, you get pocket with extremely high probability. In other words, finding your keys took square root of n steps instead of n. That's Grover's algorithm, a quantum way of searching that's quadratically faster than anything classical.